It's a real pleasure to have our neighbor. I apologize for that.
We all butcher each other's names. We just have to be accepting of this.
Anyway, who will talk to us about harmonic maps?
Thank you. Okay, so first off, thank you very much for the invitation. Also, thank you for that lovely picture of me in a tuxedo you put up. So, I'm hoping this to be a pretty low-key talk. And honestly, I don't know the timing of this at all. There's every possibility we're going to get through what we get through. I'm just going to say thank you at some point and we'll be done. The goal of the first part is to kind of just introduce everyone to nonlinear harmonic maps and what's known about its regularity theory. Much of the early part of this has extremely analogous formulations for other types of nonlinear PDs, right? So most of the types of structures that appear and the proofs for that matter that appear are things that occur for a whole host of nonlinear PDs, and I'll name a few of them. And the second part of the talk is going to focus on more sort of recent stuff, where I'm going to talk about a type of singularity formation that can occur from not a single solution of this nonlinear equation, but from sequences of them. It turns out the types of singularities that can occur from sequencing is different and can occur on bigger sets than what can occur for a single solution of one. And we're going to try to, what you get out of this is something called the defect measure. The defect measure kind of measures the amount of energy blowup that's occurring for sequences of solutions. And the energy identity is basically this conjecture that says that, well, we should know exactly what this thing looks like. Like this thing should have a form that we really understand. And so the main result that really we'll get to maybe understanding what the statement is today is a proof of this with Daniele Valorta in the last couple of months. Okay, so we got outline. So we're going to talk about linear Laplace equations first, right? So this should hopefully be a little classical, but I want to phrase things in a way that'll motivate how the nonlinear case will be phrased, because how you say everything always matters when you kind of switch from one point of view to the other point of view. So I'll try to say it in a way that works. I'll give you lots of examples. Almost everything here, like my definition, with the exception of one slide of definitions, which I kind of regret, all definitions will be through examples, and I'll kind of say, look at this example, and the definition is this with lots of epsilons floating around. We'll talk about nonlinear maps in particular after I give some examples of various nonlinear Laplacians that kind of have a similar feel. And we'll talk about regularity properties, singularity properties, so forth and so on. And then finally, we'll discuss bubbles and defect measures, so the type of blowup that can kind of occur throughout the sequence. And again, mostly this should be through just understanding some basic examples and seeing what happens and hopefully wrapping our head around, what's the general phenomena behind all this. I won't get to a proof outline. That's just impossible. Okay, so background, linear harmonic maps, right? So what do we got? So we have a function. It's on a ball in Euclidean space, and it takes values in R, and we say it's harmonic if it's Laplacian, which is to say the sum of its second derivatives vanishes, right? It's the standard harmonic equation. As written, right, this makes sense for C2 functions. And one of the first things you kind of try to sit down and do when you're trying to find actual solutions of this thing is to rewrite it so it doesn't depend on so many darn derivatives, because it turns out to be much easier to study and even prove the existence and analyze these things if we can remove some of them. And the standard trick one always does for this is you're going to take your solution of your nonlinear equation, and you're going to multiply both sides by a cutoff function phi, right? Some smooth whatever function. You're going to integrate by parts with this, right? So that instead you're going to get that Laplacian of u is 0 if and only if the integral first with respect to every cutoff function phi of the gradient of u dot gradient of e is 0, and the so-called weak formulation. And the main observation to make about this is the fact that that right-hand side there only depends on one derivative of u, right? Even just in an integrable way, in fact, not two derivatives, right? It requires a much less information. And if you're even, slightly more clever and integrate by parts one more time, then you can show both derivatives on the Laplacian of your cutoff function. And what's kind of interesting about this, even abstractly speaking, is that u doesn't even need to be a function for this. Right, you can talk about a distribution, right? Something that has no notion of a value whatsoever, being harmonic by simply asking that when you apply the Laplacian of any test function, you get 0. And so that's called the distributional formulation, right? And so this top line requires that u be an H1 function, and the second line just requires that u be a distribution. Not much at all. I don't think my zooming in really works. Okay. So how can we characterize linear harmonic maps, right? Well, what are different ways of kind of saying this? And how do we say this plays a crucial role in the nonlinear theory? Because I'm going to give you 3 ways of sort of understanding when something is linear harmonic. And it turns out that in the nonlinear context, these are not the same thing. All right, they're the same thing for linear guys, almost obviously so. But the fact that they're not the same in the nonlinear case is super subtle, especially some of them. So take an H1 function, for instance. Okay, so first derivative is an L2. And the following are equivalent. U solves the Laplacian of U equals 0 in the weak sense. So the description from the last slide. And so in particular, it's harmonic. It solves the Euler-Lagrange equation, right? It solves this equation. 2, it's a critical point of a functional. So it is the critical point of the so-called Dirichlet energy function, right? Just consider any function v whatsoever. Look at its energy, so the integral of the gradient of v squared, right? And if U is a critical point, which basically means that if we vary it by any family of solutions, take the derivative, we get 0. All right, then being a critical point of the energy functional is the same as solving the Euler-Lagrange equation, Laplacian of U equals 0. Right? So you could also be a critical point of a function. And finally, in this particular context, being a critical point of the Dirichlet energy functional is actually the same as being a minimizer of the Dirichlet energy functional. This is basically because in this context, this is a quadratic function. It's a non-negative quadratic function. Like your critical points don't have a lot of behaviors they can have except to be minimal, essentially. You can prove it more directly if you want, but that's the information. And so fine. Any 3 of these things are the same thing for a linear harmonic function or for just a function to R if you want. But if we're talking about functions with values in another manifold, which we're going to do in just 1 second, actually all 3 of these things are different. The fact that being a critical point of the energy functional is not the same as a minimizer is maybe not shocking. It's a nonlinear functional. You're going to have critical points of various indices floating around. The fact that being a critical point is not the same as solving the Euler-Lagrange equation should be more surprising. And what's going to end up happening is that, well, we'll see that. Do I write it? No, I don't write it. Well, we'll see that being a minimizer implies being a critical point. That's kind of clear. Which implies solving the Euler-Lagrange equation, but the opposite directions are not true. In particular, solving the equation is much worse than being a critical point. The regularity properties of a solution of the equation, as opposed to the regularity properties, something which is a critical point of this functional, are vastly different, right? In some sense, solving the equation is the wrong thing. You don't want to do that. You want to be a critical point of something. It's the functional that matters, not the equation. Let me point out something real quick, because this is sort of an emphasis of what you want to do in the nonlinear case. For linear elliptic PDEs, right, the main result you build to after all of our classical books at the end, right, is the fact that whether I'm talking about a weak solution or a distributional solution or whatever, it's a smooth solution, right? So once you have a solution in any sense, it is a smooth solution and it's effectively smooth. So if it lives in L2, it actually lives in H1, it lives in HK, it lives in C infinity effectively, meaning that, if on some, analyst effective always means the following. It's on some ball, you have some estimate, that on a smaller ball, you have every other estimate that's better than that. And a goal will be to do something similar in the nonlinear case, but there'll be restrictions because singularities will appear. Got me, by the way. Okay, so nonlinear Laplacians. That's our crash course on linear Laplacians. What are some examples of nonlinear equations? And in particular, things that are nonlinear Laplacians, to be exact. So not a nonlinear Laplacian is the Monge-Ampere. And that's a nonlinear equation that doesn't feel like a Laplacian at all. Right? So the following all feel like Laplace equations with nonlinear terms. So one good example is a minimal surface. So if the mean curvature of your surface is 0, then you can understand this as being in a variety of ways, actually, but you can understand this as being a nonlinear Laplacian because, for instance, the Laplacian of the coordinate functions vanish. Now, because this is an intrinsic Laplacian, that's inherently a nonlinear condition. You can also rewrite this, by the way, as being a nonlinear harmonic map, which is also an isometry. This also gives it that kind of characterization. Einstein manifolds are examples of nonlinear Laplace equations. The Ricci curvature should be appropriately viewed as the Laplacian of the metric. If you write in the right coordinates, this is actually true, but this is simply morally how you should be thinking. Ricci curvature is the right Laplacian of a metric floating around. It's a nonlinear guy because, much like with Yang-Mills, there's a gauge invariance here, which means that you're adding these nonlinear terms to compensate for the gauge invariance. which now brings the example from this morning. Yang-Mills, right? So the way you should think of this Yang-Mills equation, right? So that's the divergence of the curvature equals 0, is that if you have a connection A, that's like your function here, then the curvature of this, so that's a 1 form, and the curvature is a 2 form, it goes up in indice by 1. And you should interpret the curvature as the derivative of the connection. Hence this Yang-Mills functional being like the integral of gradient of u squared in that context. And therefore, the divergence of the gradient of A is like a Laplacian. And if you actually pick good coordinates, it looks literally like a Laplacian, as always, with some nonlinear terms below it. Actually, the regularity theory for these guys all have similar fields to them with their own subtleties that kind of float around. And then, okay, a bunch of others. Nonlinear harmonic maps, biharmonic maps, nodal problems, Q-valued harmonic, they're parabolic versions of all this, so forth and so on. I'm mentioning this because most of the early regularity results I'll mention have versions in these contexts as well. And they all kind of have their own subtleties, but they follow a basic scheme that we can go through. But now, our focus. Nonlinear harmonic maps, what are they? Okay, so start with the following. Take a function, pretend like it's smooth just for the sake of argument. You can get around this, it doesn't matter. Between two manifolds, right? And usually I restrict myself to a ball on one manifold because that's what analysts do. So between M and N, two Riemannian manifolds, right? So they have geometries. Then, so for instance, I could be talking about a mapping U from a ball, let's say in just Euclidean space itself, to the sphere, S2, which I can view as living inside of R3 itself if I want, right? So I've got a map from one manifold to another manifold. And FYI, letting M here always be Euclidean space doesn't matter. That doesn't really affect what's going on here. It's the N not being Euclidean space where chaos really gets caused. The derivative in this case is what, right? So if I have two manifolds, if I have point X, then the derivative du or gradient u doesn't actually matter the way I'm saying what I mean by this. It's a mapping from the tangent space at X to the tangent space at Y, u of X. So it's du of X, capital X in the tangent space at M, and this guy's in the tangent space, u of X and N, right? Pushes forward, tangent vectors, right? And it's a linear mapping, right? So I've got a linear mapping from here, from X to u of X. And if these are both Riemannian manifolds, then if I have a linear mapping between these two linear spaces with norms on them, I can look at the norm of that linear mapping. Note, by the way, in the case of the sphere example, that this derivative is literally just a partial derivative, viewing this thing as being embedded inside of R3. So if I can define the norm of this mapping from X to u of X, then I can define Dirichlet energy, right? I can look at the integral, the norm squared, and there you go. You got some energy associated with this guy. But now, what do we mean by being a nonlinear harmonic map, right? And we can mean one of three things, and we really want to distinguish between these three cases. We can be weakly harmonic. So we can solve the Euler-Lagrange equation of being a critical point of this Dirichlet energy function. So in this case, you get like a standard Laplacian, but you get a nonlinear term that's like gradient u, so it's similar. This A, by the way, is like the second fundamental form if I asymmetrically embed my inside some other Euclidean space. You can rewrite it about 6 different ways. So it's a nonlinear Laplacian. So you can solve that weakly. That's one thing we can ask. So in the sphere case, you get the fun equation, which is the Laplacian of u is minus the gradient squared of u times u. Second thing we can ask. So we call it stationary, and this is actually not usually the definition of stationary, but it'll actually, it's easier to present it this way. If u is a critical point of the energy functional. So subtlety. If you solve the Euler-Lagrange equation and you're smooth, it turns out you are a critical point of the energy functional, right? So all the arguments that you're used to from standard linear whatever analysis work. If you're not smooth, what's going to happen is you're going to realize at some point you're taking more derivatives than you're allowed to do. And you're going to ask yourself the question, is it the technical issue or is this a real issue, right? And the answer is it's a real issue. There are solutions to the Euler-Lagrange equation that are not critical points. Morally, what you're missing are so-called domain variations and other ways of varying solutions, basically by instead of usual Euler-Lagrange equations come by changing the image by adding something on, taking DDT. Another thing you could do over here is take a one parameter family of diffeomorphisms to get a one parameter family solution. So the image doesn't change and take DDT. Those don't recover that if you're not smooth. Those turn out to be different variations. So you're missing stuff. So you can be a critical point of the energy function. This is stronger than being weakly harmonic. And the last thing is you can be a minimizer of the energy functional, which unsurprisingly is stronger than being a critical. In general, minimizer implies stationary, implies weakly harmonic. So let's do some examples with all those nonsensical definitions behind our head. So example one. So there's two easy ways to build examples of nonlinear harmonic maps, both of which really actually appear usefully in various places. So it's the good first examples. Unlike Einstein manifolds, the first non-trivial example of an Einstein manifold is just horrendous. So we're going to try to build a mapping from S2 to S2. And the first thing I kind of want to observe here, I'm going to rewrite some of this stuff, use a lot, is I want to view S2 as CP1, right? So that is, I want to look at pairs of complex numbers, Z1, Z2, right? Not both zero. And I want to call them equivalents if they differ by multiplication by complex constants, right? So complex lines inside of C2. And this is S2. And the next thing I'm going to do is I'm going to pick two homogeneous polynomials on C2, right? So of degree D of the same, they must be homogeneous and they must be of the same degree. Thank you. But past that, they can be whatever you want. And I'm going to define a map from S2 to S2 in the following way. I'm going to evaluate this pair of complex numbers, mod, lambda. And I'm simply going to look like E of Z1, Z2. And no reality check. If I multiply both these things by lambda, then these get multiplied by lambda each instance degree D, the lambda, pull that as a lambda to the D here. This gets multiplied by lambda each and pulls out lambda to the D here. And so both these guys get multiplied by lambda to the D if I multiply these guys by lambda. So in other words, it lives in the same equivalence. Like this is a well-defined mapping, just as a reality check. And not shocking, maybe it's holomorphic, this mapping, as a mapping from S2 to S2. And then, one can either compute directly or just use the maybe intuitively clear, if not necessarily why, clear point that if you're a Kähler manifold and you're holomorphic, you actually will be a nonlinear harmonic map, which is basically to say this is a nonlinear harmonic, right? So all these guys are nonlinear harmonic maps. Just as a dumb example, although it's not so dumb if I stick some epsilons and take limits there, but you can take quadratic function, for instance. Let's stick mostly with linear. So in essence, this mapping U from S2 to S2, if it's degree D polynomials, it'll have degree D. It'll wrap around S2 D times in the course of kind of going around. And these things are stationary harmonic maps. They're smooth stationary harmonic maps. They are not minimizers. They'll actually be local minimizers, but they won't be global minimizers. They won't minimize the energy, just maybe local. Example number 2. Take nothing away from this lecture. It should be the examples, right? Example 2. There's another nifty way to build a nonlinear harmonic map. It's a little bit different than this. So I'm going to do the following. Let's take R3. Ring suspiciously is R2. Let's look at S2. Ring suspiciously is S1. And let's take the mapping from R3 to S2, takes point X and just projects it into the closest point, right? At given moments. Now this is clearly a mapping from R3 to S2. And as it turns out, it is a minimizing harmonic map, right? It's not just harmonic, it's a minimizing harmonic map, which is, by the way, clearly not smooth, right? They're the singularity at the origin, right? So the takeaway that you should have from this is that it's smooth everywhere except one point. It's a minimizing harmonic map. So there is a code-dimension 3 set, namely a point inside of R3, for which it's not smooth, and it's smooth everywhere else. Right? That's the observation we want to make. Oh, yeah. And I won't say this too carefully, but you can get a whole bunch of neat examples by composing these two examples. So if I were to take 2 to S2. Let's see what it is like. 3 to S2. If I were to take a point X, project it to S2, and compose with one of these guys, get a new map to S2, those would also all be harmonic maps. But depending on what this is, they would either be weakly, stationary, or minimizing harmonic maps. You can get all three from these various combinations. Basically, you need a certain balancing act to happen to actually do of this stuff. Those are the easiest examples of kind of weakly harmonic things that aren't critical things. Okay, so crash course and structure results about these things. So you know, if we have a harmonic map in whatever sense we mean here, if I'm doing the structure theory really carefully, I'm going to introduce to you things like stratification theory and all the rest of this, and I'm going to slide all that under the rug. I'll use the words a couple of times, and either you know it or don't. You don't worry about it if you don't. So the most natural thing to do first, it just turns out this is too simple-minded, but you can do it, and after the fact, you'll get results on this. Is you can decompose your harmonic map between your two manifolds into a regular and singular parts. And the easiest thing to do here is define the regular part as just being the points where you're smooth near that point, and define the singular points as well, everything else. Like either you're smooth or you're not smooth, right? Those are your two options. And it's actually much better to do the following. It's much better due to Federer in the 60s. But his definition is one of these definitions that it takes 15 minutes to wrap your head around because it's very cleverly defined. It's defined in a way to allow him to pull measure theory into it. And really, it's only after a lot of work that you can say it's what you want it to be. But what it's much better to do is to actually split up the singular points into how singular they are, right? We can distinguish them by saying, well, this point's that singular and that point's maybe more singular, and split it up into what you would want to call k-dimensional pieces of the singular set that maybe split them up nice. One can picture in your head, even if you don't know what that is. Basic regularity results that we know out here that are quite classical, right? Due to Riviera, Schoenwald, and Bethel. So Riviera told us the following. If we have a weakly harmonic map, so you solve the Euler-Lagrange equation, but you aren't a critical point, it turns out you can be nowhere continuous, which is simply to say you don't have a regularity theory. The singular set's everything. There are no regular points. There are no smooth points. I mean, if you think for a minute, who says there's a smooth point to your H1, solution of your Euler-Lagrange equation? And actually, the answer is, well, that may not be. However, and by the way, doing this in equation order, not chronological order of how they were proved. If you're a stationary harmonic map, then Bethiel proved, well, at the very least, you have smooth points. There actually are points that are smooth for your solution. And in fact, most points are smooth. So there's an open-dense subset of smooth points. And actually, the singular set of this thing has codimension 2. It's got at least 2 dimensions down of your space. So maybe it's points inside of R2, actually proved in -2 measures 0, if I'm being really careful. But think of a line in R3 or think of points in R2 or so forth and so on. But at the very least, there's smooth points. There is a smooth and a non-smooth piece. And Shea and Uhlenbeck proved that actually, if you're a minimizing harmonic map, you're smooth away from a codimension 3 sense. So hence our example over here. We have R3, we're smooth away from this point here, codimension 3 sense. Right? And they proved that's always true, right? In a Hausdorff sense, the Hausdorff dimension of the singular sense is always in -3. Okay. So if you're not an expert in the area, you're probably happy with these statements and you won't move forward. I think the questions that arise after you do this is, well, 2 of them. One is that Hausdorff dimension is actually awful. If you're trying to actually do anything effective or analytic with this, you really can't. I mean, there's not much you can use to do with this. And the other is, what about the structure of the singular sets? All nice pictures that I'm drawing, basically pictures, you might picture singular sets themselves as basically looking like manifolds or varieties or something that's semi-reasonable. It can break up, your SK up there should actually be a k-dimensional manifold, maybe away from a smaller piece that's sitting inside of it. And actually the correct word to use here is rectifiable, as it turns out, that this is manifold away from a set of measure 0. So what is the structure of these singular sets in the end? And so after Federer sort of introduced all this in the 60s for minimal surfaces, maybe I should add, by the way, Shea and Uhlenbeck, the real contributions up here for doing a lot of what they did was they found a monotone quantity. for the harmonic maps. And once they found that harmonic, sort of that monotone quantity, they're able to sort of take Federer's ideas and just sort of pluck them into the nonlinear harmonic map context and prove a lot of the same things. At least that was one of the contributions. So Simon in the 90s was the first guy to start to answer this question. So Leon said, and what he was able to prove was the following. So he proved that if you have a minimizing harmonic map, and if it's into some target manifold N that happens to be analytic in nature, then this top part of the singular set, this n-3 dimensional singular set, is actually n-3 rectifiable. So think manifold, for the sake of argument. This, by the way, was an outstanding proof, right? So he introduced something called an infinite dimensional Lojacevich inequality to do this. Very clever, very interesting. And then I guess the general result that we have at this point, this is with Daniele Valorta. So basically, we can drop the minimizing assumptions true for stationary. So just have to be a critical point. We can drop the fact that N's analytic, just manifolds are fine, C2 maybe or something like that. And we also get that all these stratums are K-rectifiable. So not just this top piece of the singular set, but we get that every piece of the singular set is exactly the sort of has the rectifiable or manifold type structure you expect it to have in the end. And I might add that for in the minimizing case, we proved that it's not just n-3 dimensional, but actually it's got finite algebra. So it's not just of dimension, but the measure is bounded. Actually, the solution has a priori estimates. The gradient lives in everything less than L3 weak. If you think about this example over here, this is sharp. Right? So this guy here, right? If I just compute what's the gradient of u, it's roughly like this, right? 1 over x. And how does that behave in R3? Well, it's not in L3, it's in everything less than, or it's weak L3. And then we showed this, so this holds for all solutions. This was the first time actually prior estimates were proved for nonlinear equations like this. Essentially because of the fact that Hausdorff dimension is so often, essentially. And the fact that you can't control that's what sort of stopped you from proving actual estimates from understanding dimensions of singular sets before that. Oh my. Okay. So we can reset now. I'm gonna do more examples. So what I really want to talk about here a little bit is something called defect measures. I want to talk about so we've talked about singularities here of a fixed harmonic map, right? I want to talk about sequences of harmonic maps and the types of singularities that can form there. And I might add that what I'm about to discuss has very, very close analogs for both Einstein manifolds and Yang mills. The same basic phenomena occurs for both of these things. So the setup is going to be the following, right? We're going to have a sequence. In fact, for the first statements, I don't even really need them to be harmonic maps. The harmonic map part will play a role when we're talking about what these things look like in the end. Take a sequence of mappings from some ball into another manifold, which have finite energy, right? Their H1 norm is bound. And well, if you have a sequence of functions with finite H1 norm, what can you do with them? You can basically do two things, right? Well, I jumped ahead. Never mind. So let me make the following statement first. Even in the case where M is a surface here, two-dimensional, in this case, you can prove a harmonic map is actually smooth. So in this case, you have a sequence of smooth harmonic maps of finite energy, but they are not uniformly smooth, right? So for instance, you don't have like L infinity bounds on gradients or things like this. They will blow up at places, even though each one individually is smooth. And we want to understand now, how is that blow up going to occur? What's it look like? And so let's do an example of this first. Okay, so I'm going to come back to our example over here, but choose a very specific sequence of examples this time. So again, let's start with S2 being CP1. So pairs of complex numbers, Z1, Z2. And I'm going to define a sequence of harmonic maps, epsilon of Z. So from C is how I'm going to do it, just for simplicity's sake. It could be from CP1 if you want, doesn't really matter. By that dumb thing. So So for each point here, I'm and in C, I'm going to get a point in S2 over here. If we think about what this is doing for a second, so here's our C. Then if we take Z to be really, really large, like way bigger than epsilon here, right? So somewhere out here, then F epsilon out here. So this is really big compared to that. Remember that this number here, this point, is sort of true mod, any multiplication. So I can divide by Z, and I get 1 here and like almost 0 here. So its value is almost 0, 1 inside of S2. Think of this like the North Pole, if you want. And on the other hand, if I evaluate it at the origin, then this is epsilon 0, which is the same thing as 1, 0. So over here, the value is, well, actually equal to 1, 0. So from here to here, it's going to completely wrap around the 2 sphere, right? And right around that epsilon is when it's kind of halfway around, because that's like 1, 1. So we have our epsilon here. And so imagine you take C and you kind of just wrap it around your S2, but it does it in like space epsilon, like in smaller and smaller amounts of time. So out here, and we wrap all the way around now in space epsilon, and then we come back out. So that's a sequence of nonlinear smooth harmonic maps. Interesting points about these examples. Their energy actually independent of epsilon. So they're wrapping faster and faster around, right? But if we think about what's the gradient of this thing look like, the gradient of F epsilon here is like in this epsilon ball anyway. So out here it's close to 0. And in the epsilon ball, it's roughly like epsilon inverse. But the volume of this epsilon ball is like epsilon squared. So it's a squared and a squared. So if I square that and I integrate, I basically get 1. So the energy of these guys is actually independent of your epsilon, right? This is a sequence of bounded energy harmonic maps. And if I take a limit to these guys, what's happening? Well, away from your epsilon ball is converging this 0.01. So we see it's converging here to a constant. So we have a sequence of smooth harmonic maps. They are converging to a smooth harmonic map, but they're clearly not converging smoothly. Like something off is happening here. And what we're going to want to do is try to measure how it's off in just a second in a way that we can try to capture this in more complicated scenarios where we can't write everything down. Enough people are making eye contact, I'll take it. Okay. So, how do we describe this phenomena of sort of smooth solution going to a smooth solution, but not going smoothly? And we're going to do it through something called the defect measure in this case. And actually, the definition really doesn't require harmonic maps at all. It's a really interesting kind of construction that people tend to not study all that much in generality. So take your sequence of harmonic maps, for instance, with finite energy. And let's do 2 things to it. So if I have a sequence of H1 functions, I can take a subsequence and they'll converge, but they'll converge weakly in H1. Okay? So I want to measure then, so I put my Fj, they're going to converge weakly. F infinity in the limits. And if I want to understand how is my weak convergence not strong convergence because something is blowing up, then let's look at the gradient of f of j squareds, not as functions, which they are, they're L2, I mean L1 in that case, but as measures, right? So consider this as a sequence of measures on our guy, because after passing to a limit, we can limit out both these guys. And on the one hand, we'll get our let's say 0, our weak limit of our FJs. And on the other hand, we can limit out our measures on some limit measure. And the limit measure is going to have an absolutely continuous part and a non-absolutely continuous part. And the absolutely continuous part is simply going to be the energy of your limit function here. And there's going to be something left over at the end. And whatever that thing that's left over at the end, this is what you've lost when you've gone from your FJ to your this is where blowup has actually occurred. This is where non-H1 convergence has actually occurred in our process. Yeah.
Could it be that is also absolutely continuous?
In principle, yes, but not for harmonic maps. Yeah. That's a perfectly fair question. Yes. Yeah, that's a perfectly fair question in general. Yes. Or at the very least, I don't know the answer in general, but I would imagine, yes. I feel like you can crank something out. So this singular part of this limit is what we're going to call the defect measure of the sequence. It's going to capture what's interesting here, right, is that the total integral here hasn't dropped, right? So the energy of our limit guy might be less than the energy of this guy, but we haven't made that loss here because we've limited as measures, and measures don't lose in the limit. So going back to our example from up here, right, let's ask what happens. So we've already analyzed that we're weakly converging to some constant map because outside of here, nonsense is happening. If we consider our sequence of defect measures in this case, then what's this going to limit to? Well, the limit's a constant map, you'll have a 0, but where's all this energy concentrating? So if we're away from the epsilon ball, it's basically 0. Everything is concentrating in a smaller and smaller neighborhood of the origin. So actually, we're just going to 8 pi times the Dirac delta at the origin, right? We've lost all the energy at a single point. Right? And much like last time, let me emphasize here, a point inside of R2, which is what our C is a codimension 2 set, right? We've lost everything inside of a codimension 2 set. So singularities might be codimension 3, or at least in -2 measure 0. Conjecturally, by the way, probably the best conjecture left out there for harmonic maps right now is that a stationary harmonic map is smooth away from a codimension 3 set. This is really hard for this reason here. It may be smooth away from a codimension 3 set, but it's not effectively smooth away from a codimension 3 set. Things can blow up, and analysts are bad at this. We're not good at proving things are finite if they're not uniformly finite, right? So people have not really figured out how to do this just yet. Okay. So as I just said, right, the thing to keep in mind here is that our defect measure, our mu in this case, is supported on this codimension 2 set, which is a point inside of R2. And there's a result going back to Feng, Luo, and Lin that basically says, well, this is what happens. So in particular, if I take any sequence of stationary harmonic maps for finding energy, and I look at their defect measure, so I limit out the energies as measures, so it's the energy of the limit plus whatever's left over. Then the whatever's left over here is always going to be n-2 rectifiable, right? So think it's going to be supported on n-2 manifold basically. You're always integrating on some n-2 manifold. So in this case, it's like a point inside of R2. And importantly here, okay, I'm okay. Importantly here, what that means is that, so by Feng, Luo, Lin, writing, point to it later. So it should be supported on some n-2 dimensional set that's kind of like an n-2 manifold, right? Rectifiable to be precise. And that means you're integrating the Hausdorff measure over that set times some factor in front, right? So this is the blow up set. This is where this thing is actually kind of blowing up in the limit. So it's a single point up here. And this is the energy density. So the 8 pi here, right? It's how much energy actually got lost at this point where you had blow up occurring. And we always know it looks like this. Yeah.
So in 2 dimensions, it tells me my limiting measure has just come.
Finite even, right? Because each one, we'll know, I haven't said it, but each one has to have at least epsilon energy. It's basically an epsilon regularity theorem. So finite, uniformly finite. Yeah, the rectifiable for these sort of top stratum things tend to be easier because it's on the same level as the energy. So you tend to lose a definite amount when you're doing this. So it's finite measure and everything. And let me just sort of remark on one more example. Same exact example, in fact, but just to do something stupid real quick. Let's consider a sequence of mappings of epsilon from Rm into S2. And what it's going to do here, I'm going to split my Rm as an Rm -2 cross C. And its value at xz is just going to ignore the x components entirely. Right? So I've taken my example where I'm mapping C and wrapping it around S2, and I'm adding on n-2 variables and doing nothing with them. Right? It's just totally trivial. And then in this case, we have almost exactly the same statements, right? You're still going to converge to a constant weakly because, well, it's the same thing happening on each two-dimensional slice. But your defect measure now is going to be 8 pi times not the Dirac delta at the origin, but basically the Dirac delta at this n minus 2-dimensional subspace. That then you blew off a point at every single r minus 2 along. That's a Hausdorff measure. Yes, and my one technical definition for the lecture, which again in hindsight I somewhat regret. But we're gonna do that. I'm getting enough eyesight that I'm feeling good. If I get 5 of you to follow through, I'm happy. And if you don't follow, it's this with epsilons. It's these examples with epsilons. So it turns out, this is by Feng-Wall-Lin again, that for most points of a defect measure like this, you can blow up, right, which will make precise in 2 seconds, and see bubbles, right. So that this sort of, we see from this picture here, then these smaller and smaller epsilon balls, we had an entire little ball wrapping around an S2 going on here, and that's not an accident. That exact phenomena is going to happen at least almost everywhere, like it'll almost always happen. That you basically 2-dimensional solutions outside of these blow up spots. To say that with some precision, I have to tell you what blow up means, and I have to tell you what bubble means. In the end, so let's start with the following. So take a sequence of maps from some ball into another manifold, because whatever, and some other map from all of Rm. So it's important in the second case that you're actually from a big Euclidean into the manifold again. Then we make some definitions. So we call another function f, which is a mapping from Rm into n, a blow up at a point x. I'm going to draw a picture in a second. If there's, let me say it in words, then I'll draw a picture, because the picture is so much easier to understand. If there's a sequence of points xj going to x, and a sequence of radii zooming up at that point, so that if we zoom up at the point x by those radii, we get f nullified. Your picture is the following. Here's the ball. In J is my point X. And what I want to do is I want to take a sequence of radii, which are going to 0, R sub J. And I want to think of ourselves as taking a microscope, zooming up on that small little ball, right? And seeing what it looks like. And to do that, I'm just going to take the function and just pull it back. So you steal the whole thing. You can F that out of this. So X R sub J. So I've taken this point and I've zoomed up by down to that small radius and zoomed up. And now we simply ask if I keep zooming up on this point more and more and more, or if this is a sequence of maps, if I'm zooming up on the sequence more and more and more, does this converge? Right? And if it converges, you're saying something about what the behavior of this thing at very small scales, right? What does it look like if it has, or in the case of a sequence, what's maybe disappearing in the limit? Maybe because you're seeing it pre-limits, it'll be gone in the limit because the R sub J goes to 0 here, right? It's like up and disappeared. But you're seeing what went away in that limit. So this is what a blow up is. Note, by the way, that when I zoom up more and more and more, this may have only been a mapping from the ball of radius 2, but it becomes like a mapping from the ball of radius R sub J in, right, bigger and bigger. Hence the fact that it's on all of Euclidean space. Even if the underlying guy was a manifold, right, you get Euclidean space like this. So something is simplified in this, which is always nice. And the other definition I have to shove down your throat is that we call B a bubble if it's one of these, basically. So slightly more precisely, if we can write Rn as some Rn minus 2 cross R2, and if our mapping B, which is from Rn into N here, ignores the first n minus 2 variables. So it turns out it's only a function of 2 variables, 2-dimensional guy. And the 2-dimensional function that's left over is actually a finite energy harmonic map. So it looks like one of these. So it's a bubble if it's actually just if it's on an m-dimensional solution, that's actually a 2-dimensional solution with finite energy. The reason it's called bubble, by the way, is that you can conformally compactify your R2 to an S2 and get a harmonic map from S2 into N. Hence, it's an S2 sitting inside your N, so bubble. And we call B a bubble at some point X if there's a sequence of solution for your sequence function f sub J, if there's a blow up for which your bubble actually arises. And, a priori, there's no reason to think that would ever happen, right? But the point is going to be, of course, it does. And actually, by Feng-Wall Lin, if you take almost every point of the defect measure, there is a sequence of bubbles that associate to that point in the defect measure. So bubbles always occur. In fact, they generically occur. You expect them to. The example over there, it's almost a bubble, right? In one line, it'll be a bubble. It's going to be a bubble after I take f sub epsilon, we scale the ball of radius epsilon to 1, and it'll become like a constant sequence of mappings. And that limit, which is just the same thing for all epsilon, that'll be the bubble. So up to terminology gets a bubble. I'll do that carefully now. So classic bubbling. So your question exactly. Consider the sequence, f sub epsilon going on up here. So on radius epsilon, it just wraps around your S2. Consider the followings for this sequence of maps. Like x sub epsilon just be the origin, because why not? And the r sub epsilon, the epsilon. Next. And then a fun computation here is that if I took the ball of radius epsilon and rescale that out to the ball of radius 1 and all this, we have we blow up that our mapping f epsilon at scale epsilon, then what we get out of it is actually just 1z, independent of epsilon, right? So in other words, we're going down, but when we scale it back up, actually it's a constant sequence. So it certainly converges to something because it's just actually constant. But what it converges to is just itself, which will call the bubble. So the bubble here would be the 1z that comes out of it. And let's reimagine something up here. So if this is our bubble here, which we got by taking this sequence, which we basically just did something stupid to, right? We blew it down and we blew it back up in order to see it. This factor here in front of our Dirac delta, it isn't just anything. It's actually the energy of this bubble. It's 8 pi because they were all 8 pi, no matter what epsilon was, times this Dirac delta. So the energy associated to this blow up point was exactly the energy of the bubble at that point. And that's not an accident, right? The conjecture here is that what should always happen. The energy at the points of blow up should be precisely equal to the sum of the energies of the bubbles at these points. And Feng-Wall Lin proved there's always these bubbles. And then based on Uhlenbeck and Taubes and what they did for actually pseudo-holomorphic maps on surfaces, the conjecture became that for almost every point of your blow up set, this E of x, this factor that's actually in front that you're integrating, is exactly the sum of the bubble energies at that point. And I think what I'm going to do is skip the more complicated example because we're never going to get to how I use it anyway. And talk a little bit about background on it, just so I can be fair to everybody who did stuff. Yeah.
So would the conjecture be, general, it's SK. You can have some energy that's another K for different Ks. I mean, like here you wouldn't see sort of the higher Ks.
To get something to concentrate on SK, you basically need something that's an energy on the level of K itself, Sn minus K. You need to be like an integral gradient of u to the K, which may not be finite. So the only place this can really happen is on this top level, which isn't for a fixed singular set anyways, for the sequence. This is why it disappears in the limit anyway. Right? So they can sort of build on this n minus 2 set, but then they're gone. And this phenomenon doesn't quite happen for the lower dimensional subsets. Okay. So some literature on this conjecture. So let me start with surfaces, because this is where a lot of the early work was on. So if I have a harmonic map from a surface into some other manifold n, then the first real results were due to Uhlenbeck and Taubes, where they were really interested in symplectic manifolds and Gromov-Witten theory. And they proved the energy identity held. So if you're solving this first order equation, it turns out to be, there's almost something topological about this in the end. You can basically measure all this energy in a way that lets you sort of count it in a very simple way. So one can actually produce this. Same thing happens in Yang-Mills, by the way, if you have instantons for the energy identity conjecture. For first order equations, it tends to be easier. The first time it really got proved for all surfaces was by Parker and Yost. These are separate papers. Parker was quite a few years before Yost there. They should have individual dates on them. And it was proved for approximate harmonic maps by length for surfaces. And that's actually that's more recent. For general manifolds, right? So Lin proved that the lower bound always holds actually. So this guy's at least as big as the sums of the bubbles at this point. Intuitively, this is totally clear. Like you blow up each of these guys, you lose them in the limit, so their energy should be lost in the limit. You basically just need enough structure to make that intuition careful, and he really built the structure. I mean, that's why it's fair. He built the structure to make this a careful statement. So really, you're trying to show that you don't lose more than the energy coming from these bubbles. That's really what you're afraid of in all this. There might be regions in between these bubbles for your solutions, and you're afraid they're holding some energy. Even if they don't kind of locally hold energy, they might sum up to holding energy over the whole thing. This is really where all the challenge is. If the target is a sphere, then Lin and Riviere proved this in O2. And actually, more generally, they did something quite neat. What they really proved is the target is a sphere, then you have an L1 bound on the Hessian. And in general, if you have an L1 bound on the Hessian for your sequence of solutions, they prove the energy identity holds. So they reduce the energy down to the sort of L1 Hessian conjecture, which they prove for spheres. And then, how am I doing? I'm good. I have 2 minutes. I can do 2 minutes. Okay. So it actually turns out this problem got solved first on Yang-Mills. So Daniele and I solved this so it got proved for instantons by Lillenbeck, and it proved in dimension 4. So this is the corresponding like surfaces for Yang-Mills. This is the critical dimension by Riviere. And then Valorta and I proved this for Yang-Mills about 5 or 6 years ago. But what I should add is that proof absolutely 100% no way works here. Every part of it breaks down for surfaces. It's very frustrating. If I were sort of to give an answer as to why, I would say the following, and this never like literally appears, but I think it's morally the correct answer. If I look at a Green's function in dimensions 3 or higher, it's like polynomial. If I look at a Green's function in dimension 2, it's log. And that means that any estimates that one kind of has where you're expecting decay and growth and things like that somehow morally build on how a Green's function might behave, they just don't work in dimension 2. Like nothing really works. So our proof here is actually quite different. And then I'll just state the theorem. So the main theorem for today's lecture, which hopefully we understand the statement now, and I'll be very, very satisfied if that's true, is that if you have a sequence of stationary harmonic maps with bound energy, you look at the defect measure of this guy by Lin, then for almost every point, there's a finite collection of bubbles such that the energy density of that point is exactly the sum of the energy. And for technical people, you only really need basic like C2 geometry or something for these guys. I should probably add our proofs is horrifically quantitative. So we don't really prove this. This is a corollary. What we've proven out, honestly, I think it's a much more useful result anyway, is we take individual solutions, not sequences, and we really break them down into regions in a very effective way that either look like bubbles or they look like regions between bubbles. And we can control everything on these guys individually in a very quantitative, sharp way. And when you simply apply it to a sequence, this will pop out, but there's actually much more useful information that's there. But stating it just takes forever. It's not worth it. Okay, I'll go. Thank you.
Is it expected that the defect set has better regularity than the
You should ask Leon Simon. They built these really nice examples for harmonic maps. For minimal surfaces that show that if the target is analytic, I would say absolutely. I would guess it is probably going to be like a variety or something like that. If the target's just smooth, I feel like one might be able to cook something on. If that in there is just smooth and not analytic, I worry you might be able to cook up an example. That's basically what Leon Simon does for minimal surfaces.
But in his example, I guess he also needs to modify the event.
Well, it's a minimal surface. They're kind of the same. That's right. Maybe both have to be analytic. I'm being real handy. But I mean, I think if you assume something like that, it's certainly conceivable that you would have better than just rectifiable. I'm skeptical if you're just. I wasn't skeptical before Leon Simon, that's why I'm emphasizing. Like, the results surprised me.
Questions?
What if it says something about Einstein equations, so this theory for harmonic maps and.
I don't know if it says something, there's a corresponding conjecture for the Einstein equation, which hasn't been solved yet, right? So there's a corresponding energy identity there, and that one's now still open. But to be honest, if you ask me why it's not solved, I couldn't answer that offhand. I'd have to rethink about it from the beginning. There's some subtlety floating around that I don't remember. My feeling would be it's technical. But their like L2 curvature bounds aren't even like the natural monotone quantity. So everything is worse there. Like even proving finite L2, right, is quite a project for much less control. Yeah. So I think, when they're doing this for pseudo holomorphic maps, that's kind of exactly what they want. They want to consider the spaces of pseudo holomorphic maps from a surface into something else. And they want to know what the boundary points of that are. And they want those boundary points to themselves be a moduli space. They glue all these things together. So that's exactly why you want this in some sense, is that you want to be able to put these things together. To rephrase it that way would take more work, and that hasn't been done. But that would certainly be why you would care about something else. Thank you.